Previously, we've talked about an interference pattern. When light goes through two or more slits, the light waves that emanate from those slits interfere with one another on a distant screen, causing constructive and destructive interference, giving the bright and dark patterns that we see, which is indicative of light being a wave, not a stream of particles. But what happens if you have just a single slit? We talked about diffraction in the previous video as well, how diffraction is a bending of light around edges and obstacles. Well, if you have a single slit, you have two edges. So light, according to Huygens' principle, being a wavefront, being a series of smaller point sources that create a new wavefront, you have a bunch of tiny dots here, dot point sources that all act as wavefronts. So what will happen is the edges of the slits, basically, one way to think about it, is they interfere, creating a type of interference pattern. We're not going to call it an interference pattern, though, because we already established that that's with two or more slits. We're going to call this a diffraction pattern because the interference it produces is caused by the diffraction of the waves around the edges of the slit. So what does a diffraction pattern look like? Well, a diffraction pattern actually resembles a little bit of an interference pattern because, again, it's due to interference. You have a central bright peak, but you have these secondary, very faint peaks. Unlike an ideal interference pattern where all of the peaks have the same brightness, that actually doesn't happen because in two-slit interference problems, each slit acts as a diffraction pattern as well. So, but in an ideal case, if you ignore the diffraction in a two-slit interference problem, each of these maxima should be exactly the same value in an interference pattern. In a diffraction pattern, that's not the case. You have a very bright central m equals 0 maxima, and then you have a bunch of very faint secondary maxima. Another difference, I won't go through the derivation here, your book talks about it a little bit, is what you're measuring when you compare the equation for a diffraction pattern to our previous equation for an interference pattern. The interference pattern, we had two equations. We had one for the maxima location or angle of the maxima for the two-slit interference pattern, or you could use the value with the m plus 1/2, which gives you the minima or the dark spot locations. For a diffraction pattern, we only look at the minima. So the m equals 0 is always a maximum. There is no minima here. But m equals 1 corresponds to the first minima on either side. And again, your book uses +1 for here and -1 for there. Most books don't do that. It doesn't really matter. You have m equals 2 is the second minima, m equals 2 is the second minima on either side, then m equals 3 would be up here, m equals 3, m equals 4, m equals 4, and so on. Again, those are the order numbers. So the angle is measured from the perpendicular to the center of the slit. So here we have this angle would be, let's call it theta 2. It's the angle of the second minima, second order minima. If we want to know what that angle is, what the location of that second order minima is, we use this equation. Now note, it looks almost identical to the equation for the interference maxima. The only difference is the variable d. Previously, we used a small d, or your book uses a small d. That's the slit separation. That's the distance between the centers of the slits. How far apart are they spaced? Here, this capital D is the slit width. Remember, we only have one slit here, so there's no separation between two slits. There's a single slit. We need to know how big is that slit. That's capital D. So they both use D's, which is confusing. One is lowercase, one is capital. So it's important in your notes to keep those, clear. Angle is the same. Angle is measured from the perpendicular between the distant screen and the slit, measured from the center of the slit. M is the order number, but here the order number refers to the minima locations. And lambda, again, is the wavelength of light that we're using. So are we using yellow light, blue light, red light? You'll get different values depending on the wavelengths of light that we use. And the restriction again here is M must be 1, 2, 3, 4, 5. It cannot be 0. Unlike the interference pattern where it can be 0, for diffraction it cannot. This equation gives the location or angle of the minima of a diffraction pattern. There is no equation, you're not given an equation for the maxima of the diffraction pattern. It is not just simply adding 1/2 to the m term like we did for the interference pattern. It's a bit more complex than that, and we don't get into that in this text. So here's an equation that gives you the location of the diffraction minima. It looks very similar to the equation that gives you the interference maxima for a two-slit interference pattern. That is an important distinction to make. The small d version of this equation gives you the maxima location for an interference pattern. This equation that uses a capital D gives you the minima, the small d gives you the maxima in an interference pattern. The big D gives you a minima in the diffraction pattern. And then, of course, you combine these when you look at actual two-slit interference. We'll be doing that most likely in lab. If you have lab with me, we will definitely be doing it. But if you're not doing lab with me, then you'll probably work on some similar experiment. So this gives you the diffraction maxima. Now, the wider this slit is, the smaller the angle of the minima. And what ends up happening is you end up having all the light just going across like the particle method. You just see one big bright spot and the rest disappear. As this slit gets smaller and smaller, this diffraction pattern gets wider and wider, and you can clearly see the width increasing as the slit decreases. And I will link 2 applets that you can use that play around with both the two-slit interference pattern and the one-slit diffraction pattern by changing the wavelength, changing the slit width, and seeing what happens to the maxima and minima locations as you do that.